Hello, we are looking at partial fractions in this lesson of today. We are looking at in this lesson today. What is partial fraction about? We we are familiar with fractions, algebraic fractions that can be added together, give us a single fraction, as in the case we have here. Okay, now looking at a fraction such as this, we have 7x minus 1 all over x plus n over x minus n. Now that is a fraction that could result from the addition of the fractions on the right hand side. That could result from the addition of fractions on the right hand side. I'm talking about the addition of these two fractions could give this. Assuming we know the value of a and the value of b, or the value of a and b are given, and that of m and n are also given. We can sum them together to give us this fraction on the left hand side. The fraction on the left hand side is a compound fraction. A single fraction of this kind, we can refer to it as a compound fraction, and I'll refer to these separate fractions that can be added up to give us this particular one on this side as the partial fractions, or the fractions that are written in parts and then summed together to give us what we have here on the left hand there side. So fractions of this kind on my right hand side are often called partial fractions. Now the process of expressing the compound fraction, in this form is called partial fraction decomposition. Decomposition means the process of splitting up. Into parts. That's what we call partial fraction decomposition. Now we have rules surrounding or that guide us to how we break down our compound fraction, which is of this kind, to look like this, which we have regarded here as partial fractions. Now the rules depend on the kind of denominator that the compound fraction comes up with. So for example, the compound fraction here in this first has denominators that are linear expressions. X plus m is a linear factor, x minus n is a linear factor of the entire denominator that we have here. So we have now come to conclusion that the denominator of a given compound fraction determines what the partial fraction will look like. So if we have compound fractions such as this that has linear factors, we express this partial fraction in this form: a over x plus m plus b over x minus n. Of course, if we have another linear factor in addition to what we already have here, for example, if we have actually maybe x plus r in addition to that, then we're going to be having another part added to this. That would be having c divided by x plus r. So that will give us the partial fraction decomposition for this fraction that has linear factors. So let's take note of that. Number 2 is the kind of fractions where we have the denominators as repeated linear factors. In this case, you can see that we have the factor x plus m, and we also have another factor x minus n in brackets squared. We have two factors there, One of them is x plus m, and the other is x minus n all squared. But the x minus n is a repeated factor. That means we have x minus n coming twice. So how do we express the partial fraction of this kind that has repeated linear factors? Because the factors are linear, of course, we're going to have a over x plus 4 in this case. Sorry, this is should have been m. So this should have been m. So we have x plus n, and then we have the next to be b over x minus n. And the last will be c over x minus n to the power of 2. Now, if this were to be power 3, if what we have here is actually 3, if it was 3 and not 2, then we'll have a fourth fraction to complete this as a probably p. Choose the letters for our constants at the top. So that would be x minus n to the power of 3. If it has power 4, we keep writing the fractions in the power or in the increasing power of that particular factor that repeats itself until we get to the particular, let's say, z over x minus n to the power of r. If we have the power here as r, so we keep writing all the fractions in increasing power of denominator for the particular factor that repeats itself. So that gives us the case of denominators with repeated linear factors. We are going to stop there. Okay, let's take a look at the third one. So we might have to solve a problem on this third one. Now the third one has denominators with quadratic factors. Quadratic factors here means that you have a factor that has the power 2. And in this case, the factor regarded as quadratic factor is such that it cannot be factorized. So let's see what this looks like. We have this particular example here in my left-hand side. Having denominators x minus m as a factor and s squared plus n as a factor. But you will notice that the x minus m is a linear factor, while the s squared plus n is a quadratic factor. So how do we express this or split this up? The rule for splitting up a compound fraction or a rational function like this kind that has a quadratic denominator as its factor, denominator, please. How do we split that up? Now I have a over x minus m. Why do I have a over x minus m? Because we have first a linear factor coming up. So that's what gives us the a over x minus m. So the other part that has the quadratic factor will be written in this manner: bx plus c over x squared plus n. That would be the form of the composition for a fraction or a rational function of this kind, to give us its partial fraction in my right hand side. So what if what I have is looking like this? Let's say we have x over x squared plus 1 as a given compound fraction, and I'm to split this up into its partial fractions. The process of decomposing this will look like this. If we have partial fraction of this kind, remember there is no linear factor in this case. The one we had here had linear factors, In this case I've written now, there is no linear factor. We just have s squared plus 1. So how do we decompose this into its partial fraction? Its partial fraction will look exactly like this. Let's say we have bx plus c over x squared plus 1. Remember that there is no linear factor, so I won't be writing a plus, and take note, it is not true. It is not true that it must be bx plus c. So let me go again. If I have the compound fraction in this form, let's say we have 1 over x squared plus 1. Remember, this denominator is a quadratic denominator, which is non-factorizable. It cannot be factorized. So the composition will look like this: a x plus b. Why am I rewriting this? Just to tell you that you can choose whatever letters you want to write for your constants. You can choose whatever letter you want to write or use to represent your constants. So this is the exact form of the composition for this particular kind of a compound fraction or rational function. Now the last one is denominators with degrees higher than the degree of the numerator. We will look at that in subsequent lessons, but we are going to take a look at some examples, and I'll run through the one that we have already worked out before now. So let's take a look at an example that we had looked at something similar to before now. The question says resolve 7x minus 1 over x squared minus x minus 6 into partial fractions. Now the first thing I have to think about is, if this fraction here has the denominator that is quadratic, the question I'll ask myself is this denominator, which is quadratic, is it factorizable? Oh yes, it is factorizable. So if it is factorizable, then I have to rewrite it in this manner. Of course, I have 7x minus 1 over x plus 2 multiplied by x minus 3. So confirming that it is factorizable, and I went through the process of factorizing, gave me what I have right there. So what I have right there now, you can see, is the factorized form of this denominator that we have here. So definitely, I will now decompose this or split this up using the rule for the rule that applies to denominators with linear factors. So if I'm using the rule that applies to denominators with linear factors, how would that go? How will we get that solved? How will we get that solved? So remember, if we are going to do that, then it means that we have to write in this form a over x plus 2 plus b over x minus 3. So if I'm working this out, I can decide to use any of these methods. One, I can decide to find the LCM of this. If I find the LCM of of these two, that will give me x plus 2 times x minus 3 times x minus 3. So using this to divide my LCM, it gives me x minus 3. Gives me x minus 3. So x minus 3 times the numerator here, which is my a, gives me a times x minus 3. Then if I use x minus 3 to divide my LCM, this will strike out, x minus 3, so that I have x plus 2. So x plus 2 times my b here, that will give me b times x plus 2. Now, if I have now written this as a single fraction, equating it to this side, meaning that the right-hand side and left-hand side are both equal now. We have single fraction on the right-hand side and single fraction on the left-hand side. And the denominators, being that the denominators are the same, it therefore means that the numerators can be equated. So I can actually equate this to this. I can equate both of them. So this and this definitely are going to be equated and set to be equal. So doing that, I'm going to have to write 7x minus 1 equals a in x minus 3 plus b in x plus 2. So simplifying this, we give us simplifying that will give us ax minus 3a plus bx plus 2b. Now, I had solved this earlier on I solved something like this earlier on. So working out the constant, the value for the constants, we get a as 3 and b as 4. Now, I really want to focus on this part of work today, denominators with repeated linear factors. How do we get this solved? We have the problem 3x squared minus 3x plus 12 over x plus 4 minus, multiplied by x minus 2 squared. We have to resolve these into partial fractions. So how do we get these solved? So we take the process right away. All right, so if you remember how we said we split up our compound fraction of this kind or this manner, having a repeated linear factor at its denominator. So we have x minus 2 as a linear factor that is repeated, and the method we said was the right method for decomposing such kind of fraction is to have not just a constant on top of this part, but to have the constant with the factors repeating in increasing power of what you have here as its repeating denominator. So what we mean is that this would have been written as a over the first linear factor there is x plus 4. So I have written that as the first part. Then the other part that is repeating, that will have the form b over x minus 2 squared is repeating itself twice. X minus 2 is repeating itself twice. So I'm going to have the first part of it having the power 1. So we have x minus 2. Sorry, this is supposed to be x minus 2 to the power of 1. Then we have plus c over x minus 2, this time around to the power of 2. So that's the end of it. If it was to the power of 3, of course, we are going to have another fraction added to that. So this is what we are going to be working with. And we are going to be finding the value of the constants a, b, and c in our partial fraction that we have written here. So moving on, let's see how this has been written. Okay, this is exactly what I just wrote now. Now, how do we come about what we have here as a single fraction? It's by simply working out the LCM of all these. Working out the LCM of all these, we can have that as x plus 4 times x minus 2 squared. The LCM will give us exactly what we had here in the beginning. Now we begin to use each of the denominators to divide through the LCM. So if we use x plus 4 here to divide through the LCM, it will strike out this. And if it strikes out that, we have x minus 2 in bracket squared, multiplying our a. So we have a x minus 2 squared. If we use this to strike out, if we use the denominator of the b to divide through our LCM, if you strike out one part of this, of course, we strike out one part, this actually would have been, let me write it out. So this would have been x minus x plus 4 times x minus 2, then times another x minus 2. This is what the denominator actually looks like. So if we use this to divide the denominator. This, we strike out one of that. Then we strike out one of that. So we have x plus 4 times x minus 2 remaining. So that multiplies b on top. So we have b times x plus 4 times x minus 2. Then if we do the same thing in the last fraction that we have there, we have x minus 2 in brackets squared. This, we strike out this, and then this is gone. So what we have there is x plus 4. X plus 4 times the numerator, that would be c times x plus 4. So once again, observing that the denominators, the fraction on the right hand side is equal to the fraction on the left hand side. We have single fraction on the right hand side and a single fraction on the left hand side. It means that the numerator of this fraction is equal to the numerator of this, and the numerator of this is equal to that. Of course, it's confirmed. The numerator of this is the same as that. So therefore, we can equate the numerators of the fraction. So equating the numerator of the fraction, we have 3x squared minus 3x plus 12 equals everything on the top. So that's what we have right here. Now the next step is to try and eliminate one or two of the constants that we have. For example, in this case, we have x minus 2 in the bracket. So if I let x be equal to 2, this will turn out to be 2. So I have a 2 minus 2 plus b 2 plus 4 plus b 2 plus 4. Then I have the same thing for these two also. And then substituting x there, we have 2 there. Simplifying all of it, 2 minus 2 will give us 0. So this whole will disappear to 0. And this part of it, 2 minus 2 is 0. So everything, this is 0, everything here, multiplying that 0 wipes out. So everything here disappears to 0. It's only this part that we have 2 plus 4 that would not disappear. So we have 6c. So that's what we have right here. So we have 6c, and then simplifying all of that. Remember that on the left-hand side, you're also supposed to substitute the value of x as a 2. So simplifying the left-hand side and the right-hand side together, we'll be able to come up with the value of c as a 3. So that gives us the solution for c. In the same way, we have substituted x as 2. We can also do the same. Look at this, x plus 4. We have x plus 4. I can let my x be equal to minus 4. So if that's minus 4, I can eliminate b and then try to work out another variable. So if I let x be equal to minus 4, let's see what that comes up with. So substituting x as minus 4, what happens? We'll have here as minus 4. We'll have here as minus 4, and this whole part will turn to 0. So that will disappear. If we have x as minus 4, we have this whole part also turning to 0. If we have here as minus 4, that will give us a minus 4 minus 2. So that will give us a minus 6. So we have minus 6 squared, that will be 36a in this part. And this part is the only one that wouldn't go to 0. So all these other parts turns to 0. So we are able to, we are left with a, means that we can now calculate for our a in this case. So let's see our write-up on that and see what. So like I said, we have 72 equals 36a in the simplification, and then gives us a as a 2. Now, the way to find our c, the way to find our b, we have let x be, let's go to the beginning again, we have let x be minus, we have let x to be plus 2, which helped us to find our c. We have let x to be minus 4, which helped us to find our a. Now we are left to finding b. Now you pick a simple value for x that can help to easily simplify and get the final constant. In this case, we are here to get b. So I'm going to pick a value for x, and I'm going to pick a value which is going to be very simple enough for me to get my answer easily. So I'm going to pick the value 0. So if I pick 0, I'm going to have 0 minus 2, so that gives me a times minus 2 squared plus b times, remember here is 0. So when you substitute 0 all over, you're going to have this equation 12 equal to 4a minus 8b plus 4c. You can pause the video and see how we came up with this after simplifying from this line here. So we have 4a, we have 4a, we have 4a minus 8b plus 4c. Remember that we already have a value for a, so you substitute the value for a. We also already have a value for c, substitute the value for c also there, and that gives us a 4 times 3 and a 4 times 2 effectively on the side where you have a c and b. So c and the a. So working that out, we'll be able to calculate the value of our b, and b value becomes 1. So all we need to do now to round up our solution is to substitute these values for a, b, and c into our initial partial fraction that we have splitted the given question into. So we have splitted this as a over x plus 4 plus b over x minus 2 plus c over that. So we substitute the values for a, b, and c. If you do not do that, then you have not done any, you have not even answered the question. So doing that gives us this as our final answer. Now, lastly, we're going to look at denominators with quadratic factors. Factors that are quadratic in this sense means the factors that can no longer be factorized beyond the quadratic expression that it gives us. So in this case, we have resolve 2x squared minus x plus 4 over x cubed plus 4x. Can I factorize this denominator? Taking a look at it very well, can this denominator be factorized? Of course it can. Factorize x cubed plus 4x, that will give us x. Then we have x squared left, so we have x to the power 2 plus 4. So it can be factorized. Now this part of it is linear, but this part of it remains quadratic. So we have a combination of a linear and a quadratic factor. Now the quadratic determines here in this case that we are going to be splitting using the method that, or using the rule that applies to quadratic factors, using the method that applies to denominators with quadratic factors. So how do we do that? Remember that will be looking like this. We're looking like a over x. Then we have plus the quadratic part of it. We take the numerator as bx plus c over x squared plus 4. So the quadratic factor part, which is this part, will take the numerator bx plus c. That is how we split our compound fraction, or the fraction that is given to us, and then we go on to simplify and then work out the values for a, b, and c. Now let's see how that goes. So we have this as I've already written. Now the method I use here is different from the one above. You can use the same method for the one above, but I've used a different method here so that you can know that we can have up to 3 or 4 ways depending on what manipulation you come up with. Now, what I've done here is that I decided to multiply through all fractions on the left and the right hand side by this denominator. I decided to multiply through by this denominator. So you can multiply through by this denominator. If you do that, you're going to have x in x squared plus 4 multiplying from the left hand side, and on the right hand side, we're going to use to multiply each of the fraction on the right hand side. So I've written here also to multiply a over x, and I've also written here to multiply bx plus c over x squared plus 4. Now, in working or in trying to simplify, what happens? This x squared plus 4 strikes this x squared plus 4. Then we have for this one, x here is cancelled by this x here. This x and this x will go. So leaving us with a x squared plus 4 times a. So that's what this gives us here. Then if this and this are struck out, we have bx plus c left multiplying x. So that gives us what you have here. Then on the other side, of course, the whole of this strikes out the whole of this at the bottom. So this is another method you can use. For the earlier solved examples, you get the same result. The same result means that you come up with this numerator and then you have to equate both of them, having simplified to the point where denominators are written as a single denominators. Having simplified to the point where the denominators are written as a single denominator. So what you have now is what we have is what we are seeing right here. So the next step is to open up our bracket. So if we open up our bracket, we have a times x squared, that gives us ax squared. A times 4, that gives us 4a. Then we have bx times x, that gives us bx squared. And then we have c times x, that gives us cx. Now the next step is to collect the like terms. We have ax squared and bx squared as similar, so we collect them together because they are s squared terms. So we collect them together, that will give us a plus b all in brackets times x squared. So we have a plus b all in bracket times x squared. Then we have 4a. Of course, let's write the cx first. We have cx, then we have plus 4a. All right, so it cannot be simplified beyond this. Now we will compare the coefficients. You will notice that this is an s squared term. If this is an s squared term, it means that this is the same thing on this side. So we call this particular expression now, we call it an identity. An identity is such expression or equation such that we have everything on one side exactly equal to what you have on the other side. So what you have here is an identity. So we're going to compare the coefficients of the parts of the expressions that are having the same power of x. For example, we have the 2x squared term on my left hand side, the 2x squared term on my left hand side, this one, exactly the same thing as this one here. So I'll come again, this one is exactly the same thing as this. Okay, all right, so this is where we are. This is where we are, right where we are. So we have the 2x squared term here, exactly the same as this. So comparing the coefficient of x squared in this case is the bracket a plus b. So therefore, a plus b is exactly going to be my 2. A plus b is equal to 2. I can call that my equation 1. Then I observe that we have an x term here. The x term here is minus x, and the x term here is plus c. But plus c here definitely will mean my minus 1, which is the question of my x here. Or you can definitely write, you can decide to write minus x is equal to cx. Then of course the x strikes out on both sides so that we have minus 1 equal to c. That's another way you can do that. Then for the last part, we have 4. Of course, we have 4 on my left-hand side here, equal to the constant term here. This is the only constant term we have, so we have equal to 4a on the other side. So dividing both sides by 4, we're going to have 4 strike 4, then we have 1 equal to 4 strikes the 4 here, then we have that as our answer for A. So the answer for A is gotten, the answer for A is gotten, the answer for C is gotten. All we need to do now to find our B is to substitute A into this particular part, which is this our equation 1. So substitute A as 1 1, we'll be able to solve for b. So solving for b, we're going to have 1 plus b equal to and b equal to 2 minus 1. So that gives us the answer for b as 1. So a is 1, b is 1, and c is minus 1. Therefore, our partial fraction will be in this manner: 1 over x plus x minus 1 over x squared plus 1. If you go back again, looking at what we have in the beginning, we are splitted in this form: a over x plus bx plus c. We are splitted in that form. So all we need to do is to stated in this form. So all we need to do is to substitute the value for a, b, and c. A is 1, so we have 1 over x. Then we have b as we have gotten b as 1, so that will be x. 1 times x, that will be x. Then we have gotten c as minus 1, so that gives us minus c. All that over x squared plus 4 in brackets. So that is the solution for this particular example. You can pause the video at any point, or you can go over the whole lesson again and see how clear this can be in a second view. When we meet again, we will be looking at the remaining two parts. We'll be looking at the remaining two parts that has denominators with okay, we are left with just one part that has denominators with degree higher than the degree of the denominator higher than the degree of the numerator. We look at that part that has degree of the numerator higher than the degree of the denominator. In such case, we call that kind of fraction an improper fraction. Until then, see you again.